So let's take a look at question 4. We are given this curve and the area between that curve, x equals 4 and x equals 0. Again, I think that should have been included in the question, so I've added that in there. And we're rotating that region about y equals 1. So this line. And so again, I had to use that equation to draw out an approximate shape for the curve. And you can see that when x equals 4, y equals 1. So you can see that the two lines and the curve intersect at that point. And the other important thing to see is that this curve is symmetric about the line y equals 3. So it kind of has that, so kind of just goes, straight from from this point down to that point. And that's because we have this quadratic, right? It's symmetric about y equals 3. The square in that expression gives us symmetry. All right, so looking at this problem, because we have a very nice expression for x, I would like to chop this region up along the x direction. And so that's going to be parallel to the axis of rotation, which means we're going to use the shell method. And so for the shell method, the expression for the volume is 2 pi times the integral of radius times height. So if this is the point y, then the radius is the distance between that point and the axis of rotation. That's why I have y minus 1. And the height is just given by the x coordinate. So that's just the x value. And that's why I just plug in y minus 3. So that's the x value. So I just plug in y minus 3 the whole square. And now you could just multiply this out and use a product rule. I found that it helped me to do a little bit of a u substitution to make that quadratic term a bit easier. And then I could replace the y minus 1 because y is u plus 3 and then y minus 1 is u plus 2. And now this thing was easier to multiply, sort of FOIL out and apply a power rule to. And then I went back to y's, plugged in the original endpoints, and then I got this expression for the volume.